All right, welcome everyone to lab number 4 of Math 155. By now, you should have seen in your classes what a limit is and what continuity is, what we mean by limit and continuity. You should have seen, well, from pre-calculus, you should know what asymptotes is, especially vertical and horizontal asymptotes on a rational function. And again, a rational function is a function that looks like a polynomial divided by another polynomial, like what I have up here. You should have been, you should have seen already in your lecture what a removable continuity is, or and what a discontinuity is, what it means to not be continuous. You should have definitely seen piecewise functions, um, and what it means to be continuous at a point for a piecewise function, and you should understand uh, what happens when a function is discontinuous on the left and right side, and what the left and right side limits are at a particular point, especially of a piecewise function. So these problems will definitely help you look at these concepts, and we will be exploring these concepts in more detail than what you do in your lecture class. Now, not necessarily with the same theory. We're not going to be covering much theory here, but we are actually going to be just exploring what happens when we have very large cases that becomes very difficult to do by hand. Very time consuming. So the first thing that we will do is we will attend this problem number one, that has to do with limits and continuity. Well, the first thing that you need to make sure that you do when you are on Maple is to make sure that you are using math mode. Right now, I am on text mode. On text mode is, as the name suggests, just for writing. I need to be on math mode if I want to actually write equations and so on. So part A of problem 1 asks me to define a function f which takes x to the rational function or the rational expression given. So that will be on Maple. To define a function, we begin with first the function name. So in this case, the function name is f. And then to actually define the function, we use colon, equals, and then dash, and then we use the greater than symbol to get this arrow. Now, one thing that is missing is the actual x. So once again, that is colon equals x dash greater. So this is how you define a function that takes x to an expression. This allows us to actually evaluate values of f at x. And our particular function is given by x minus 3 divided by 2x squared minus 5x minus 3. So once I press enter, you'll see that I have in fact defined f to be that particular function. So I have that f is x minus 3 divided by 2x squared minus 5x minus 3. Now part B asks me to graph the function of f. So I will take part B. There's more stuff in part B, but I will first take part B into pieces. So the first thing is to plot it. So to plot the function, we use the plot command. That is plot parentheses. I already defined what the function is, so I don't have to write everything again. I don't have to write x minus 3 divided by 2x squared minus 5x minus 3. All I have to do is write f and close the parentheses. So once I press enter, I will receive what the plot of f is. Now we could see that f is indeed a rational function and it has a vertical asymptote. If you look at the function f, as the x values approach this value right here, they are going up to plus infinity on the y-axis. And from the left side of the function, as the x values get really close to whatever this value is right here, the y values are going down very quickly to minus infinity. Now, the second part of the question is to determine the asymptotes of f by using the graph, and then to describe the left and right hand limits at x equals minus 2. So right now, the graph of f is zoomed out. I'm looking at it from minus 10 to 10. I do not want to look at it from so far away because I'm trying to focus on whatever this point right here is, this value, where this vertical asymptote is occurring. So for me to zoom in or out of the function, I will put comma on the plot after f, and I'll put x equals, and then I'll define the points that I want to be close to. So I'm gonna say, let's say this is -1, so let's go from -1 to 1. So what I did was I put -1 dot dot 1. So this is all from lab number 2. We know that we can do this. And I received an error. Oh. All right, sorry about that. So make sure that when you are doing this, you have f of x. Sometimes if you're just plotting it, you don't need to put the x in here. But if you are trying to zoom in or out, then you definitely need to have f of x in here. So now I could clearly see that the value of the vertical asymptote occurs at negative 0.5. I could even get closer than that. I could decide on the right side of the function to zoom in, let's say, at negative 0.4. And then we could clearly see that it is indeed 0.5. And you could keep on alternating. You could go to 0.6 and get even closer, and so on. So we could see that clearly the vertical asymptote does occur at negative 0.5. Now, we are also asked to describe the left and right hand limits at f of x equals negative 1/2. So if you look at the limit from the right side as you approach negative 0.5 or negative 1/2, you can see that that limit is going to, as I mentioned before, to plus infinity. So you could determine that the limit from the right side as x approaches negative 1/2 is going to be plus infinity. On the other side, from the left-hand side, as you approach negative 1/2 from the left side, as you get closer and closer to this negative 0.5, the y values are going down to negative infinity. So the limit from the left side is negative. Now, by now, you should know, well, we'll get into that in a second, but by now you should know how to actually determine this. You should be able to by looking at a function, tell what the right-hand side and left-hand side limits are. So on Maple, we can easily plot any function we want, especially any rational function, and visually determine that. Now for part C, let's try to evaluate the function at x equals 3 and then x equals negative 1/2. Now, in the function that you get for your lab, you may not have an error, but I probably will have an error here. So if I evaluate it at f equals 3, now because I already defined f up here, as you can see it has a 1 here, that means this is my first function. Because I already defined this, I don't need to define it again, and I don't need to write it again, I don't need to plug in. From lab number 2, we know that if I just do f of 3, I should be able to get the value. Now, notice that when I put f of 3, I get numeric exception error, division by 0. So I cannot actually do this. The question is, why is this happening? Why did I get an error? Well, let's try to do f of negative 1/2. So let's do f of minus 1/2. If I do f of minus 1/2, I get the same error. So again, I have division by 0. Now, if you look at the actual function, if you look at the rational function, you could tell that this is a rational function. What happens with rational functions is that their domain, you have issues in the domain of the function when the denominator equals 0, because you cannot divide by 0. So what's happening is that whenever you plug in 3, or whenever you plug in negative 1/2, we are getting division by 0 here. How can you check this? Well, you could try to factor the denominator and see why this is happening. So the denominator is 2x squared minus 5x minus 3. That's 2x squared minus 5x minus 3. And this is a new command. I don't think this was in lab 2. So if you want to factor a polynomial, you can just write factor. And as soon as you press enter, you see the factors, the actual factors. Now, if I was to solve now, I mean, we could do this visually. You could clearly tell that if I plug 3 here, it's going to be negative. And if you solve here for x, you're going to get that x equals negative 1 over 2 when you equate that to 0. But if you actually solve this, much like we learned in the previous lab, in lab number 2, if you do 2x plus 1 equals 0 and you solve for x, you will see, in fact, that the value that makes this equation or this factor equal to 0 is negative 1/2. And I'm not going to do x minus 3 because you could visually see that if you put in 3 here, you're going to get 0. So that is why we're getting these errors, because whenever we plug in either value into the function, we are dividing by 0. So that means that these values are not part of the domain. And remember, whenever we have this, we have vertical asymptotes. So when do vertical asymptotes occur? They happen when you divide a rational function by 0. Now, part D is to figure out the limit of f as x approaches 5 by looking at the graph. Now, let's look at 5. If we look at 5, well, one thing that you could clearly do is, from class, you know that the first thing you should do when checking for a limit is to just plug in the number. Try to do the plug-in method. If I plug in, I get just 1 over 11. So I already know that the only two values that make the function 0 are negative 1/2 and 3. So I do not need to worry that f of 5 is going to give me an error. Now, if we were to plot f close to 5, so let's do x equals 4 to 6, then at 5, you could see that we are a very small number right here. And that number is namely 1 over 11, or 111. Finally, I'm asking you to explain why f is not continuous at x equals minus 1/2 and to find a function that is the same as f away from minus 1/2 but is continuous at f minus 1/2. From class, from your lecture class, you know that for a function to be continuous at a particular point, in this case x equals negative 1/2, it means that the left-hand side limit and this is the left side. The left-hand side limit and the right-hand side limit are equal. For the function to be continuous at a point, it means that the left-hand side limit and the right-hand side limit are the same. In this function, we can clearly tell that they're not the same because we have plus infinity on one side and negative infinity on the other side. It will be a different story if they were both going up to infinity or down to infinity. You know, in that case, you still have a vertical asymptote, but now you could at least say that the limit is either plus infinity or minus infinity, depending on which case you're looking at. So the limit would exist. Here, the limit doesn't even exist at the particular point. So we definitely have a discontinuity right here. F is not continuous at the point x equals negative 1/2. Now, on to problem number 2. For problem number 2, we have to define a piecewise function f that is x squared plus 5 whenever x is less than or equal to 0, and x whenever x is strictly greater than 0. I want you to plot f, and then using the graph, find the left hand and right side limits at x equals 0. Finally, evaluate f at 0 and determine if f is continuous at that point. And if there's discontinuities, then determine if the left and right hand side limits exist. So we have a piecewise function, and let me just go back up. It's x squared plus 5. So to do a piecewise function, we just write piecewise, then open parentheses. I usually open and close both of them. Now the first thing that you put in your inside of the parentheses is the condition. So here the condition is that x is less than or equal to 0 for x squared plus 5. So I'm going to do x less than and then the equal sign, and that makes it less than or equal to 0. And the rule is x squared plus 5. Then for the other piece of the function, we have that the function equals x whenever x is greater than 0. So whenever I'm strictly greater than 0, the function equals x. So again, you put in the condition, and then you put in the rule. When I press enter, I have my piecewise function. So the piecewise function is x squared plus 5 whenever x is less than or equal to 0, or x whenever, well, this was greater than, not less than. Oh, okay, yeah. Whenever x is greater than 0. So let me show this. All right. So now, what do you have to do? Well, the next thing to do is to plot it. Now, if you notice, I did not actually wrote this as a function. I could have just done some k or whatever. But I'm gonna try to see if I could plot this like this. So what I did here is a shortcut. So the percentage symbol takes the last thing that you computed and puts it in as an input. So when I use plot percentage, then it takes this last thing that I just computed and it puts it in here without me having to type it. So I get the piecewise function here. It is x squared plus 5 whenever x is less than or equal to 0, and it is x whenever x is greater than 0, or x is positive. And the question is, using the graph, find the left and right side limits at x equals 0. Now, for me to actually view the graph at that particular point, if you notice, I actually cannot see it. I could try to zoom in. So let's zoom in from -1 to 1. All right, maybe I should have. That is the one thing. Maybe you should name this. I'm gonna name it K, such that you could actually see it. So now I can just plug K. Remember, K of x K of x equals -1 to 1. So now when I look closer at the neighborhood, I can see that if I write along the left-hand side of the graph, that is x squared plus 5, then as I get closer to 0, as I get closer to the y-axis, I'm getting closer and closer to 5. So the limit from the left-hand side seems to be 5. From the right-hand side, as I approach 0 from the right-hand side, the values are getting closer and closer to 0. So I could determine or conclude that from the left-hand side, the limit is 5, and from the right-hand side, the limit is actually 0. Now, the final step is to evaluate f at 0. So we could do eval, or we could do eval, or we could just plug in. And this actually not f, this is k. I have k at 0, and this is going to give me 5. Now, why does k of 0 gives me 5? Well, 5 is bigger than 0, so I'm using the x rule, not the x squared plus 5. And, well, I'm lying. 5 is, well, I'm super lying. I'm plugging in 0. So I'm plugging in 0. So I'm less than or equal to 0. So when I plug in 0 for x, I just get back 5. That's what I want to say. So if you plug 0 for x squared, all you get is the 5. So that's why k of 0, you get 5. Now, the last part of the problem is to determine whether f is continuous at 0. The answer to that is no. We could clearly see that, from the left-hand side, you go up to 5, and then you go all the way down to 0. For a function to be continuous to that particular point, I cannot pick up my pen at any time. If I was drawing this by hand, then from when I get to here, I have to pick up my pen and then begin down here. So it's not continuous. The correct way to say that is the limit from the left and the limit from the right are not equal. If the limits are not equal at that particular point at f of x, then the limit or the function is not continuous at that point. Now, finally, we already did this, is to determine which left and right side limits exist. And again, they do exist, and they happen to be 0 from the right side and 5 from the left side. And that takes care of that problem. Finally, for problem number 3, is to define a function cosine of 1 over x. Then plot the graph of f, zooming in and around this particular pi values. Okay? And we need to plug in so the function graph looks very nice. It's not going to look very nice the first time you plot it. So that is cosine of 1 over x. So let me call it L. So L is a function that takes x to cosine of 1 over x. Now let's plot L. If I plot L, this is what it looks like. From the left-hand side, it looks like it's constant. From the right-hand side, it looks the same, and then it very rapidly goes down, and then it begins to go up and down extremely quickly. It's going up and down so fast, and that's why it looks so squished in there and so red, because it's just going up and down, up and down, up and down very quickly. So let's actually zoom in at this value. So the values given were 1 over pi, 1 over 10 pi, and 1 over 200 pi. So let's go from x equals 0 to 1 over pi. You got to put up capital P for pi. Another way to do it is to look at the expressions here. If you look at the left side, you could go to common symbols, and then you could see pi. If you hover over it, it tells you how to put it in. So that's capital PI. So if we look at the function cosine of 1 over x from 0 to pi, you could see that it begins to smooth out the closer we get. But then look over here. It's very red. Everything is very close together. Using the same function, let's look at it from 1 over 10 pi. From 0 to 1 over 10 pi. Now, from 0 to 1 over 10 pi, you could begin to see how it opens up a little bit. It looks like an instrument of sorts. And finally, from 1 over 200 pi, you can't even tell that they're actually separated. It just looks all red. So this is what I'm asking you to do. And this is something that if you were to do it by hand, it will be very, very difficult. It would be almost impossible. Now, the next part of the problem is to pick two numbers that are very close to 0 and then plot f in a very small neighborhood. You should be able to zoom in close enough so that the function looks nice and smooth. So let me take that same function that I have named L, and let's zoom in around 0. So I'm going to zoom in from -0.0 0.0009999 to the point 0.000000999. Well, that's not small enough because I don't have a smooth curve. Yeah, if you notice the there's even though I'm making the values very small, you just can't see anything here. I mean, nothing looks smooth at all. So hopefully in the graph that you get, things will actually look smooth. Like if you look far away from here, it does look kind of smooth on that side. But there's no, I mean, I made the value so small, and you still couldn't determine, um, you still couldn't see a smooth curve, which is insane. I mean, look, I make this has 3 to the times 10 to the power negative 17. That's a very small number, and you still cannot see many white spaces. So everything is very close together here. Finally, state 3 values of y that occur in your graph no matter how much you zoom in around 0. So what are 3 values that no matter how much I zoom in around 0 always appear? Well, one of them is 1, the other one is 0.5, the other one is 0, the other one is negative 0.5 and negative 1. In fact, I could pick any 3 numbers between 1 and minus 1, and they will always appear here. No matter how small I may zoom in, they will always appear. And that is because we know that sine and cosine, both of them, oscillate. They go up and down, up and down, up and down in their period. That concludes lab 4. Again, lab 4 is due next week. And to save lab 4, I'm using the virtual console, since I assume that most of you will be. You click on File, then you click on Print. Please save it as a PDF. So change this from Microsoft XPS to Foxit PDF Reader. You could do this the same way with the regular Maple outside of the virtual console as well. It's the same steps. Then press OK. And let's say I'm going to name this Lab 4. And just make sure that you are saving it to the desktop. Right now, I am on desktop, so click on Save. And now I see it here. And then the next step is for you to go onto Blackboard. So make sure you go to Blackboard. And make sure that you open your lab. If you open your lab, you will see it as a PDF so that you can make sure that you're not sending me anything blank. Then go onto Blackboard and put in your credentials here. Go to my credentials. And finally, go into the class. So regardless of which class you're in, whether you're in AO5 or AO2, the same steps. Click on course materials, and then once you see the lab, just click on where it actually says lab. So to download the lab, you click on the attachment, but to submit the lab, just click on lab, and then you click on browse my computer, and then you could take the lab and submit it from the computer. Just make sure that you go to desktop once you are here. You should be able to. Let's see. Yeah, desktop. And then you can click lab 4. You can also upload it to Google Drive or Dropbox or OneDrive for your own personal keeping, and then click on Browse Cloud Storage. If you click on Browse Cloud Storage, a page will eventually pop up and you'll be given a way of submitting it. Thank you for your time.